In the previous video, we introduced the idea of inequalities and did some practice and talked about interval notation. In this video, we're going to dive deeper into the idea of inequalities and present to you your first really powerful tool called the boundary method. Now, this class is called Precalculus, and this tool called the boundary method is really the first thing that we're going to learn in this class that has direct applications to calculus. It's extremely useful. So let's think a little bit deeper about what an inequality is. Okay, so this is an example from the previous video. And I can, because I am a mathematician, if I have a statement like this, where it's relating one quantity to another, I could say something like y is equal to negative 7x plus 4 divided by 3, and y is equal to 6. I could just break this up and graph it, kind of get a visual representation of what's happening here. And that's what I've done on this graph on the right. Okay, this red line is y is equal to negative 7x plus 4 divided by 3. A more familiar way of looking at that might be negative 7/3 x plus 4/3. So we have our y-intercept here at about 4/3. Well, not about 4/3, but 4/3, and a slope of negative 7 to 3. So that's the red line. Now the line y equals 6, the blue line is just a horizontal line at y equals 6. And the answer to this question, right, if we just look at this, when is the left side greater than the right side? Well, it's when it's above the right side, right? When the red side is above, for y values, above the right side, which is the blue line. So our answer to this then, if we carry this down, it was negative 2 right here. So anywhere from, for our x values, negative infinity, like, way out here, all of these things were true because for any value for x that's, to the left of this intersection point right here, we have a true statement. The answer, by the way, was negative infinity to negative 2 in interval notation because we had open parentheses here because this is not an or equal to sign. And so we kind of have this test, right? If we have this intersection point, or we can identify where this point of interest is, and then test kind of on either side, I could easily come up with the answer. So we're going to expand on that idea, expand on that thought a little bit. And it's called the boundary method. So looking at a little bit more complicated of an example here, if I had this inequality, x squared plus x minus 6 is less than 0, first of all, you should be able to graph that. That's just a parabola, and its vertex is, right here, okay? So if this is asking when is that quadratic, when is that parabola less than 0, it's talking about when is it negative, right? When is it under 0? So it would be all the x values that correspond to those like red points right there. And because it's an or equal to, I would say, look, well, that's a negative 3, right? And that is 2. So it's everywhere between negative 3 and 2, non-inclusive of the 3 or the negative 3 or the 2, because it's not an or equal to sign. So if we could then, for any inequality, identify where are these points, like where's that point and where's that point, then we can do a method called the boundary method, and it works like this. You take your inequality and you manipulate it, meaning you move things to the left or the right side or whatever. You set it to 0. So for example, if I had given you x squared plus x squared plus x is less than 6, our manipulation step would be to subtract 6 from both sides and get x squared plus x minus 6 is less than 0. Now, you don't have, this is not necessarily a requirement for the boundary method, but it helps greatly because it's very easy later on to deal with 0 over here as opposed to a different number. Okay, so just for this class, we're setting it to 0, okay? At that point, you're going to do something called identify critical points. Now, what is a critical point? Okay, this requires some thinking here. If we have, for example, this one, our critical points were at negative 3 and 2. What are those for this parabola? They're zeros. Okay, so a 0 is a classic example of a critical point. We have a change in behavior on the graph. We're going from you know, with relation to 0, we're going from being greater than 0 to being less than 0 at critical points. Okay, if we had, in the previous example, we had 6 on the other side of the inequality, so our critical point kind of was not with respect to 0, it was with respect to 6, and there was that one value, it ended up being -2. Okay, now the classic, so basically that's it. A critical point is, and this is sort of the math definition, is a possible change in behavior of the graph. It's possible because the behavior doesn't always change at a critical point, but it tends to. And there's an extra situation here. These minimums and maximums, or relative minimums and maximums, they fall into the critical point category if we're thinking about the broad definition. But for the purposes of inequalities and stuff, for what we're doing, we're just looking at either zeros or another thing that you know what they are because you've taken like trigonometry and algebra at this point, where you can have changes in the behavior of a graph. And we'll see one of those, example of one of those in a minute here. So let's try an example. Let's actually do this example. So we have x squared plus x minus 6. This is already, the first step is already done where we've manipulated it and set the relation to 0. So what we're going to do next is factor it. We factor it because factoring allows us to easily identify critical points. Okay, so how do we factor this? You could say that x plus 3 times x minus 2. Okay, and that is less than 0. That's just factored. The zero product property would tell us if this was an equation, if it was equal to 0, we would say that x could be -3 or x could be 2. Those are our critical points. So our critical points are at -3 and 2. So on a number line, this is how the boundary method works. Okay, once we've got our critical points on a number line, we're going to put those critical points on the number line. And then we're going to kind of section our number line off into regions. Okay, these critical points represent the boundaries of these 3 different regions here. Okay, we have like region 1, region 2, and region 3. And what we're going to do is we're going to select a value that is somewhere less than -3, so somewhere in region 1. Select a value that's somewhere between -3 and 2, so in region 2, and then a value that is greater than 2 in region 3. And I'm just going to so it doesn't matter what you pick, but you should pick numbers that are like easiest for you to compute. So for example, let's say we're going to test at like -5 here. Okay, and this is what you do. You come back to if you do have a factored form of your equation, come back to that one, and we're going to plug -5 in for x and see if our equation is true or false, or our inequality is true or false. Now what's great about setting this thing equal to 0 is you don't even have to actually plug the number back in. You just have to know how positive numbers and negative numbers multiply together. So if we're plugging at -5, so -5 plus 3 in this first parentheses, that's going to give me -2. It's negative, right? So this is for testing of region. If we plug in -5 into the second parentheses, -5 minus 2, that's negative. A negative number times a negative number is a positive number, and then you'd have, is a positive number greater than 0? Positive number greater than 0? No, that means this is false. That means there will be no shading in this region of this section of the inequality of the number line, and it's not part of our answer. So let's pick a number in region 2. If you can pick 0, if 0's in there, always pick 0. It's the easiest one. Okay, so now we're looking at region 2. You don't have to have this set up all organized like this. You can just kind of do these quickly. But if we're plugging in 0 in this first parentheses, it's going to be +3, so it's positive. If you plug in 0 to second parentheses, it's going to be -2, which is negative. A positive number times a it's not writing negative. Times a negative number is a negative number. Is a negative number less than 0? Yes. So it's true in region 2. And then pick a number in region 3, so maybe we'll pick 3. So if we plug in for region 3, we're plugging in 3, we'd have, just to write this out, 3 plus 3, we'd have 3 minus 2. Okay, I know that this is 6 and this is 1, but it's a positive number and a positive number. Positive times a positive is a positive. Positive numbers are not less than 0, so this is no, this is false over here. So where do we shade? We shade where it's true. It's this part, okay? And because it's not an or equal to, there are open circles here, right? Or they're parentheses, either way you want to do that. Then to finish the problem, you just write the answer in interval notation. So it's -3 comma 2, which is what we saw on the graph. Okay, now let's go a little bit more, kick it up another layer of difficulty here. So factoring more horrible looking things, right? This is a cubic, okay? Something that you can do right away here is divide everything by 2. So I'm going to just rewrite this immediately as x cubed minus 5x squared minus 9x plus 45 is greater than or equal to 0 if you divide both sides by 2. So now I'm going to look at these two terms. In the first two terms, I can factor out an x squared. And if I do that, I'm left with x minus 5. I can factor out a negative 9 from these last two terms. If I do, I'm left with x minus 5 is greater than 0. So then I have x squared minus 9 times x minus 5 is greater than or equal to 0. X minus 3 times x plus 3, because that's a difference of perfect squares, greater or equal to 0. So if I have this statement that critical points are where I could have zeros, which if this was an equation, I would identify the critical points are at 3, negative 3, and 5. So I'm going to put those on a number line. Okay, I'm going to put negative 3, 3, 5, set up my regions, okay, and we'll pick numbers in these regions, and we're going to be plugging them back into this equation here, this inequality here, to see if we have true or false statements. So let's try to do this real quick. At negative 4 in this region, if I plug in negative 4, I'll have a negative, a negative, and a negative. Negative times negative is a positive, times a negative is a negative. This is going to be false. Okay, because a negative number is not greater than or equal to 0. If I plug in 0 here, just plug in 0, 0 will be negative, positive, negative. Negative times a positive is a negative, times a negative is a positive. Positive number will be greater than 0, so that's going to be true. Let's plug in like 4 for this one. 4 would be a positive, right? Add 4 minus 3 is positive. We have positive and negative. Positive times positive is a positive, times a negative is a negative. That's going to be false, because negative numbers are not greater than 0. And then if we plug in like 6, okay? If we plugged in 6, we'd have 9, so that's positive. So we'd have 3, that's positive. Then we'd have 9, that's positive. We'd have 1, that's positive. All positive numbers multiplied together to be positive. Positive numbers are greater than 0, so that's true. We shade where it's true. And because we have an or equal to sign here, it means that these are solid dots, okay, or there's these brackets. And so if we write that then in interval notation, it'll be everywhere from negative 3 to 3, union, because that's how we represent this gap, 5 to infinity, not including the infinity. And if we look at what the graph of this was, now I'm assuming we didn't have the graph to begin with, is this true? Well, we're looking at when is this thing positive? When is it greater than 0? Well, it was everywhere from negative 3 to positive 3, and then everywhere from 5 on in terms of x values. So that's what our interval notation told us in the end. Okay, so the other kind of critical point that we're going to be worried about here are asymptotes. Okay, asymptotes, as you know, are values for values where, we'll get into a more technical definition of what an asymptote is, but essentially it's a value that the equation can never be, or the graph, it tries to get really close to a thing but never quite gets to it, right? In trigonometry, we looked at stuff like f of x is equal to the tangent of x, and this had asymptotes where x could not equal pi over 2, for example. Like the tangent of pi over 2 is undefined. So when we have an undefined situation is when asymptotes come about. And why do we have undefined things ever in math? Well, it's because we divide by 0. So asymptotes would occur if we had a 0 in our denominator. So what value of x would make our denominator 0 here? Negative 3. So negative 3 is a potential for change in behavior. Notice how it was positive above the x-axis here, and then as soon as it crossed over to the other side of negative 3, it was negative below the x-axis. So that's fits our definition of critical point. It's a possible change in the behavior, in this case between positive and negative, which is exactly what we're interested in. So that's something that is now when we're presented with an inequality that has a denominator, we need to immediately look at the denominator and say, okay, when is this going to be, when would that be 0? Okay, the other critical point that we can get from this one is just 2, because if x was 2, we would have 0 in the numerator, which would give us, for this particular thing, a value of 0, which again, just like in the previous problems, when we had that the x-intercept, that was a critical point, right? We had to change from positive to negative. So let's look at this one if we change this to an inequality. So if we change this to an inequality, right, x minus 2 and x plus 3, so we have critical points at 2 and negative 3, just from what we were looking at. Now what's really important here is that this negative 3 is the asymptote, okay? And this will never be, you can never have an asymptote where it's a solid dot or a bracket. It will never include this. It will always be open. Now the 0, this will be open or closed depending on what is given to you in the problem. This is an example where it's just greater than and not greater than or equal to. So it's going to be, both of these are going to be like open circles on our number line. But let's put our number line then. Okay, here's our number line. We've got negative 3 on it. We've got 2 on it. And they're both going to be open circles or parentheses. But we don't know kind of where the shading is going to be. So that's why we need the boundary method. All right, so we're going to choose, let's say, at negative 4, and you're just going to go right here because this is kind of already factored. If I can factor this to make it simpler, then I would, but this is already factored. There's no simplification I can do here. So if I plug in negative 4 to the top, I'm going to have a negative. And if I plug in negative 4 to the bottom, I'm going to have a negative. A negative divided by a negative is a positive that is greater than 0, so we're true in this region. If I look at 0, well, 0 minus 2 is negative. 0 plus 3 is positive. Negative divided by a positive is a negative, so that's going to be less than 0, so it's going to be false in the middle. And then if I look at something greater than 2, like 3, if I plug in 3 in the top, I'm going to have 1, which is positive. And if I plug in 3 in the bottom, I'm going to have 6, which is positive. Positive divided by positive is positive, so that's going to be greater than 0, so that is true. So I shade where it's true. Okay, remember they're both gonna be open, so I'll put a little parentheses like that and a parentheses here because that will always be, sorry, the other one will be a parentheses because it's an asymptote. This is a parentheses because of the inequality given to us. The answer then in interval notation is negative infinity, not including negative infinity because you can't contain me, bro. Negative 3 union to represent this space 2 to infinity. That's the answer to that one. Okay, now here's another one. Now this the first step of our boundary method comes into play for this one for the first time. This is an inequality, but its relation is not set to 0. It's set to 2 here. So that makes it more difficult. The first step is going to be to move that 2 over. So we're going to subtract 2 from both sides. Actually, we can right away identify a critical point at 5, right? And that's an asymptote. Okay? Because we know if x was 5, we'd have it undefined right away. So boom, put that there. Okay, now we're going to move the 2 over, and we'll be left with t minus 1 divided by t minus 5 minus 2 is less than or equal to 0. Okay, our relationship is set to 0 here, but this 2 is kind of weird. I'm going to do the math. It says to subtract, so I'm going to subtract. In order to subtract, I need a common denominator. So it'll be t minus 1 divided by t minus 5 minus 2 times t minus 5 divided by t minus 5 is less than or equal to 0. So then we'll have t minus 1 minus 2t plus 10 divided by t minus 5 is less than or equal to 0. The top will clean up to be negative t plus 9 divided by t minus 5 is less than or equal to 0. Now notice how if you just took this top and it was like, okay, there's a critical point at 1, you would be wrong because that's not giving us a 0. It's giving us like a 2 or something, right? It's not set to 0. Setting it to 0 allows us to identify that our other critical point here is going to be at 9, right? Because if t was 9, looking at the top, looking down here, Okay, if t was 9, we'd have a 0 for our numerator, which would give us 0 divided by something, which would be a 0, which is a critical point. So we're going to put our two critical points on the number line. We're going to put a number line, put our two critical points on it. So 5 and 9. And we're going to test the regions. So here's the regions. Let's try at, oh, by the way, we can also say what's an open circle and what's a closed circle right now, because the asymptote is for sure going to be open, and the 0, which was the 9, is for sure going to be closed because we have this or equal to in the inequality to start with. So let's test a number that's less than 5. How about 0? Best number. Okay, if we plug in 0, and we're plugging it in down here, okay, 0, we'd have a positive divided by a negative, and that would be true, right? Because we have a negative number on the left, which is less than 0. So it'd be true over here. True. Ooh, true. True. Okay. Then between 5 and 9, so maybe like 7. If we plug in 7, we're going to have a positive number on the top and a positive number on the bottom. That's going to be positive, which is greater than 0, so that makes this false. Okay, and then lastly we have we'll pick a number greater than 9, so like 10. If we look at 10, at the top would be negative, the bottom would be positive. Negative divided by a positive is a negative. That's going to give me a number that is less than 0, so that's true. We shade where it's true, and we write our answer as negative infinity to 5, non-inclusive of the 5, union yes inclusive of the 9 to positive infinity. Okay, so that's where we end up. That's the graph. So it was asking, after we manipulated this, remember, it said we had it set to 0. So when is this thing greater than 0, or less than 0 it was, right? Less than or equal to 0. It was, all of this area, that was our, that was this part, right? And then it was all of this area, which is this part. Okay, so that's it. And in the next video, we're going to add in, or we're going to talk in general about the idea of absolute values, just equations, and then basically you'll see something like this in the next video. Okay, it'll be a question just like this, maybe. Oop, let me redo that. It'll be a question just like this. So t minus 1 divided by t minus 5 is less than or equal to 2. But then you're going to have absolute values around this. And your first step is not going to be to freak out. It's going to be just to remember what an absolute value is saying. Okay? And it's really, it is certainly, it's more difficult than this one, but not by a ton. So no worries. We'll kind of get you there. It's going to be sort of a long video, just like this one has been. All these videos have been 20 minutes. I don't know what I'm talking about. So anyway, stay tuned for that one. And if you have questions, just make sure you ask.